All right, welcome back, everybody. Now that we've talked about enols and enolates, I think we're ready to think about how these are reactive as nucleophiles. And so, what we'll talk about today is the alpha halogenation set of reactions and then also alkylation reactions. Cool. So, we'll start off talking about halogenation reactions. And if you just think about the fact that there are enols and enolates as potential nucleophiles, that should make you think that there's either acid catalyzed versions of these reactions or base catalyzed versions. And so we'll start off with the acid catalyzed version of halogenation. Cool, so here's a first example, and this will be the bromination of a molecule of acetone. Right here, and this is being conducted in a acetic acid and water solution, so acidic conditions. If you run this reaction with one equivalent of bromine, you will get the alpha brominated product here. And a mechanism for this reaction, so we always have to start out with making our nucleophilic enol, so that's that keto-enol tautomerization. After that, this will look like an alkene attack onto a molecule of bromine, but we're starting off with kind of the lone pair donation from oxygen there. Once that happens, then we end up reforming the carbonyl bond, and then followed by an acid-base reaction that gets us to the end. So alpha bromo ketone, HBr. And so an important question we can kind of ask ourselves is, well, does this initial kind of keto-enol step even make sense by pKa's? How reasonable of an equilibrium is going on here? And so if we're looking at pKa's, what we want to think about is the pKa of the acid versus the conjugate acid of the carbonyl. And so then we're thinking a pKa difference of 5 minus negative 6 is 11. And so this actually doesn't make very much sense. The formation of enol should be very, very slow. And so I'm telling you that this reaction works. And so the follow-up question should be, well, if the pKa doesn't make sense, why does this reaction work? And so the reason is that the byproduct of this reaction in itself is a strong acid. So hydrobromic acid pKa, of -9. And so if you think back to the overall mechanism up here, what you're going to get is that our acetone will sit there. 1 out of 10 to the 11 times that you look at the molecules, you'll see one molecule of enol. That enol can undergo the reaction, generate a molecule of HBr. Once you have HBr, that HBr molecule will then start to drive this equilibrium to forming enol, making more nucleophile, which can then attack, and so on and so forth. Okay, so here's a second example. And so this is a slightly more complicated molecule. Now if you look at this molecule has two different enolizable sites. Similar reaction conditions, still cold with bromine. And so here I'm showing you the two different possible products, one with the kinetic enol, one with the thermodynamic enol. And it turns out if you run this reaction, you see a 97:3 ratio in favor of the kinetic product here. When I say kinetic product, I mean that the kinetic enol is the one that's reacting as a nucleophile a little bit more often. So some hints for this came from the reaction conditions with the low temperature, making it harder to get to the thermodynamic one. Another way to think about this product outcome is to say that even if you made the thermodynamic enol, it would be a worse nucleophile. And so in the end, the kinetic one is the one that reacts the fastest. It's the form the fastest and it's a better nucleophile. Another question you can ask is, well, why don't you get multiple brominations on one of the carbons? And it turns out if we think about the product after a single bromination, so just this monobromo ketone here, and if we're trying to enolize this, we need to be able to protonate this carbonyl. This carbonyl is going to be harder to protonate because of the effect of the bromine nearby, making it the carbonyl itself a less basic carbonyl. So it's harder to enolize. Even if you were able to enolize it and you were able to get to this form of the molecule, we should expect that to be less nucleophilic because of the bromine that's sitting on there. So, kind of for the same two reasons, harder to get to the enol, less nucleophilic, we shouldn't expect any reactivity. That being said, if you take a molecule like this one right here, react it now with extra equivalents of bromine, you are able to get to the dibrominated product. And so this is kind of a nice controllable reaction in terms of how many bromines you can put alpha to the carbonyl. Use one equivalent, you'll get one. Two equivalents, you'll get two. So now that we've seen the acid catalyzed version of the alpha halogenation, let's look at the base catalyzed version. So this will be using an enolate as a nucleophile instead of an enol. So I'll give you a ketone here. React it with bromine in the presence of now base, so sodium hydroxide. And it turns out if you do that, well, we should have no reaction on the right side here. There's no hydrogens, so everything should happen on the left side. We do the reaction, and what you actually end up finding is this carboxylic acid and a byproduct here, which looks like this, so kind of a tribromomethane. It'll start to feel a little bit weird, like we broke a carbon-carbon bond. What the heck is happening? So why don't we look at the mechanism? It starts off as you would expect. This alpha hydrogen is deprotonated by sodium hydroxide, giving you the enolate. That enolate is now nucleophilic enough to react with a molecule of bromine, which is our electrophile, giving us a successful bromination product right here. And now, if we're looking at this, the question we always have to ask ourselves is, well, what is the strongest acid in the reaction mixture? And if you compare the blue hydrogens to the red ones, we should expect the blue ones to be lower pKa because they're next to a bromine atom now. And so what that means is that the next molecule of sodium hydroxide would prefer to deprotonate a blue hydrogen over a red one, giving you the bromoenolate. That's going to be your nucleophile reacting with another molecule of bromine. So overall, if you do that reaction 3 times, you'll get to the tribrominated ketone product. And now it turns out that that ketone is fairly electrophilic right here. And so another molecule of sodium hydroxide is able to attack the ketone, generating a tetrahedral intermediate, and that can collapse. But then the collapse is actually kicking out this tribromo carbon kind of as a leaving group. And you might think that's a little weird. Well, we're breaking a carbon-carbon bond. Carbons aren't good leaving groups. But it turns out if you look at the pKa of this molecule, tribromomethane, it's only 14. So actually that's a pretty reasonable leaving group, just as good as an alcohol or a water molecule as a leaving group. And so if you're thinking about the reaction I gave you, if there's only one equivalent of bromine, what that means is that there's going to be some portion of the initial reactant that never gets reacted and one smaller portion of it that gets completely converted into what looks like carboxylic acid overall. And so the natural question to ask is then, is there a way to do this reaction under basic conditions without getting multiple brominations? The answer is yes. And the solution is to pre-form your enolate with no electrophile around so that you can avoid this problem of having a more acidic carbonyl compound. And so the way we do this is with LDA minus 78 degrees. Do all of that first, get the kinetic enolate, and then you can add your electrophiles. And so at least in this reaction, what you're seeing is overall, you're going to get the alpha bromination, but you'll see there's this intermediate step of adding trimethylsilyl chloride. And so how this works is that after step 1, we should get our kinetic enolate. So again, deprotonating from the less sterically hindered side. In step 2, we are reacting with trimethylsilyl chloride as the initial electrophile. And it turns out that enolates will react at oxygen with silicon. That's giving us the silyl enol ether. And so this is just a less reactive form of an enolate. In the third step, we could then react the silyl enol ether with bromine to do a kind of traditional nucleophilic attack onto the bromine. Overall, that gets us to the brominated compound with a bromide counterion. And at the end of the day, we have to get rid of the TMS group that's still on there, and that just happens through an SN2 looking reaction like this. It's good to remember, looking at this mechanism, that a TMS group, or really any silyl group, essentially acts as an H+ in the mechanism. Alright, so that covered the alpha halogenation reactions, so both using an enol under acidic conditions and an enolate under basic conditions. And so now we'll move on and talk about some of these alkylation reactions. Let's look at a couple examples of these alkylation reactions. So these alkylations are pretty easy to understand, relatively speaking, because they're an SN2 reaction just with an enol or an enolate as a nucleophile. So here we have a simple ketone, and we'll go ahead and deprotonate it with LDA at negative 78 degrees. And then once we're confident that everything's been deprotonated, we can go ahead and add in the electrophile. So in this case, in this example, methyl iodide. So great electrophile for an SN2 type of reaction. And so overall what you're going to get is the methyl group added to the ketone at the alpha position, new bond right here. Just for completion, we'll go through this mechanism. And so we should expect that we'll start off with the ketone. We'll do a deprotonation with LDA. That gets us our lithium enolate. And then once we've added in the electrophile, it's nucleophilic attack. So kind of lone pair from oxygen collapses down, pi bond attacks the electrophilic atom, leaving group leaves. Overall netting us our desired molecule. And so here's a second example. It's going to look a little bit more complicated, but really the same thing. I'm going to give you a cyclohexanone, but with a kind of a fused cyclopropane group here with specific stereochemistry. We're going to do the same deprotonation, so forming an enolate at low temperature, and then reacting again with methyl iodide. And so looking at this now, there's all sorts of products that you can expect, but it turns out if you run the reaction, you get two major products. One of them has the methyl group on the less sterically hindered side, kind of opposite of the cyclopropane, and the other has it on the same side. You should expect, based on sterics, that one of these is easier to achieve than the other, and that's the case. So because of this wedged cyclopropane ring here, it's much easier to do your attack from underneath. So you get a 91:9 ratio. You'll notice that both of these products were the kinetic enolate, and so again that should make sense because we are working with LDA at negative 78 degrees. And just to make the point again, the stereoselectivity of the reaction comes from the initial stereochemistry and sterics in the reactant. So those previous two examples were under kinetic enolate forming conditions. So why don't we look at a couple examples that take place under thermodynamic enolate forming conditions. And so here's cyclohexanone. And so instead of a really strong base, I'm going to use a relatively weaker base, potassium terbutoxide. I'm going to do two equivalents, trying to do two alkylation reactions. And it turns out if you do this reaction, you get your two methylations happening on the same side of the carbonyl. And so if we look at the mechanism, this actually makes a lot of sense. So our first equivalent of base and electrophile all mixed together at once is just going to get us a methylation, doesn't really matter where. And the second one must be reacting again at the same position that the first one did. And so we can kind of ask ourselves why. And if you really think about the enolate formation process, because we're under thermodynamic enolate forming conditions, the enolate that's formed after the first methylation should be on this right side of the molecule because that's the more substituted enolate. So then that's the enolate for the second reaction. Okay, why don't we do a thermodynamic looking enolate formation, but in a more complicated situation. So now I'm giving you kind of a intramolecular reaction instead of an intermolecular one. These actually turn out to be very common types of reactions for forming rings, as you've seen in the past. So same thing, potassium terbutoxide, relatively higher temperature, and that should tell us this is a thermodynamic enolate forming reaction. The product of this reaction is this bicyclic compound. We won't worry about exactly how the stereochemistry works out here, but it happens to work out the way that's shown. If we go through and figure out exactly where everything is, I'm just going to number starting from the chlorine here, number all the way through. And what I see is that I can either form a 6-membered ring or an 8-membered ring. And I should favor forming the 6-membered ring, even though that's the less substituted side and the kinetic looking enolate. If we look at our product, that's exactly what happens. We made the 6-membered ring, not the 8-membered ring. And so just to help us track the reaction a little bit, we have an electrophile here at the carbon-chlorine bond, a nucleophile here at the less substituted side, and that corresponds to carbon here, carbon there. And so when thinking about this reaction, the big thing we have to remember is that we are under equilibrating conditions, so that means our thermodynamic enolate here is in equilibrium with our kinetic enolate here. And so both of those can and do exist, and it doesn't matter which one is more stable, it matters which one is able to do the next reaction. And so at least in this case, the kinetic one is much more able to do the reaction because it's forming a six-membered ring. And so this is a really important idea that the dominant species in solution is not actually the one that's reactive. And this shows up a lot, especially in these cyclizations. Before we end, I wanted to just bring up one last thing, which is that enolates are not the only types of nucleophiles we can use or see in this unit. We'll also see what are called enolate equivalents. And the idea is that even though we've been thinking about enolates, all we really care about is that we have a pi bond with an electron donating group attached, because the electron donating group then makes it more nucleophilic. And so some examples of these enolate equivalents are things like aza enolates, which are just enolates with a nitrogen atom instead of the oxygen. And so these are more nucleophilic because you have negative charge on nitrogen instead. Kind of go down the series. So again, I'm going to give you just the regular enolate we've seen, just as a comparison. And then from here, we'll move into neutral versions of these two enolate equivalents, or enolates. And so the first one is an enamine, so now a neutral nitrogen. And the last one that's really important and shows up in a lot of reactions, you've already seen one already, is the silyl enol ether. So now there's a silyl group on the oxygen. So it looks like an enol, just not a hydrogen there. Again, in terms of their nucleophilicity, I've written them in this order for a good reason. And so it tends to be the case that aza enolates are the best nucleophiles, better than enolates, better than enamines, better than silyl enol ethers. And so depending on your situation, you'll use or prefer a different enolate equivalent. And so a good way to think about how nucleophilic these are is to think about what's the worst electrophile each of these nucleophiles could react with. And so we're going to think about that in the context of these alkylation reactions. So aza enolates, again, the best nucleophile of the bunch here. They're able to do reactions with secondary halides and epoxides. And so that should make you think about SN2 reactions and how those were probably the harder SN2 reactions to do. Going down to enolates now, we're usually going to need primary iodides or bromides, so primary leaving groups. Once we go down to enamine, we'll need some sort of an activating feature, so kind of the conjugation from the allyl group. And so when we're looking at silyl enol ethers, we're going to expect even better electrophiles. And so it's most common to see the silyl enol ethers reacting with SN1 type of electrophiles. And what that really means is that we're thinking about carbocationic species. And so we'll look at just one example here just to get a sense of how these work. I'm going to start off with an enamine. And so it might look a little different to you, but it is this enamine functional group. The difference being that the two R groups are really just one big ring here. And so that's an enamine. And this is a decent nucleophile, so we'll react it with a good electrophile, so just methyl iodide here. And so we'll see the same pattern, lone pair coming down, pi bond attacking the electrophile, leaving group leaving. That'll get us an intermediate species here. So now a positively charged nitrogen. And that is called an iminium because of the positive charge. So it's an imine with a positive charge. That's not very stable, and so what this molecule does is it'll eliminate to get back to the neutral nitrogen. And so that's being shown here. And after that's all said and done, what you end up getting is actually an enamine again. And so you might be looking at this and wondering, well, why doesn't the product enamine go ahead and do another alkylation? We kind of saw this idea before. And so what we're dealing with now is that we have a weaker nucleophile in the enamine relative to an enolate, and the product is more sterically hindered. And so because of that, it's a little bit less likely to do a nucleophilic attack. And so we're able to get pretty good control, turning all the initial reactant enamine into just singly methylated product. Cool, so that wraps up this lecture. And so just to recap, what we thought about today were enols and enolates as nucleophiles. We saw them reacting with halogens or kind of alkyl halides as electrophiles, and that overall led to either kind of this alpha halogenation or an alpha alkylation reaction. Along the way, we saw a few little quirks about these reactions in terms of whether we're doing a kinetic enolate or thermodynamic enolate, what are factors that make those go different ways, etc. And so what we'll do the next lecture then is to kind of move on through this series of reactions. We'll spend some time on this aldol reaction before looking at the Claisen condensation, Macalester, and kind of more complicated combinations of all of these together.